Okay, according to my watch, it's 12:30 p.m. Pacific Standard Time. And so we're going to get started with engaging mechanics demos using the Smart Cart Demonstration Kit. That's a long title for just an hour-long webinar. Hi, I'm Dan Burns. I'm the physics curriculum and training specialist here at Pasco Scientific. Before that, I taught high school physics in the San Francisco Bay Area for 27 years and used Pasco stuff and a lot of other equipment during that time. And so I'm looking forward to sharing some of the things I've learned about this equipment today. My job title now is really just to help physics teachers. And so there's my email. Feel free to contact me with any concern, something I can do to help you with teaching physics, especially implementing a lab program, dburns@pasco.com. And I'm joined today by Glenn Starkey, our training manager, and Brandon Pruitt is our product engineer. So a lot of expertise online. We'll probably be joined by a few other people. And so I hope you have come with some questions, or if they come up, you'll give us a chance to answer them. I have started recording, and you will get a link to this recording sometime soon, the next day or two. So where can you get it? Well, you're going to get a follow-up email because you registered, and that's where the link will be. Some of you may be interested in a professional development certificate. That also will be in a link from the email, but you'll have to take a quiz first. It is a 3-question quiz. You need to get 2 out of 3 right. I'm the one that wrote the quiz, and you have my email. So if you need help, let me know. But if you're following along with us today, it shouldn't be too tough. And if you would like a copy of these slides and some of the files, there will be a link to that in the follow-up email, and I'll mention that a little bit later too. And we are using Zoom Webinar, which is a little different from Zoom meetings. Instead of just chat, we also have a Q&A panel, and use that for your questions because that'll put them in our queue and we'll have to answer them then. Not that we wouldn't answer questions in chat, but sometimes the chat will scroll away and we'll miss a question. This way it'll stay in our queue until we answer it either live or somebody will type an answer in, so that you'll see that Q&A question. And if you want to enable live English captions, you can go to live transcript and do show subtitle. This all depends on what version of Zoom you have. It's always a good idea to update your Zoom version, but that might help. And if you're going to chat, which we hope you do as well, that would be more like comments, things to add, your experience with something. Make sure you chat to everyone. And this is a problem I have. The default is to just the hosts and panelists. And that's fine if you want to do that, but every time I do it, I wanted to send a chat to everybody and I accidentally sent it to myself. So you want to change hosts and panelists to everyone. At least that's probably what you want to do. So make sure you at least pay attention to that if you're using the chat. And this is our agenda. We're looking at the Smart Cart demo kit. And there are 16 demos in it. So obviously we can't get to all those. So I picked these 5. I think we'll get to these 5. We'll see. I'll give it my best shot because they're going to show everything that's in the kit will at least be used once. And gives a good variety of the different demos in there, but there's a lot of them worth checking out the other ones on your own. The Smart Cart demo kit was a Best of STEM finalist last year, and I think it's one of the best things that you could give to a physics teacher. So put it on your gift list. It comes with a lot of things. I'm not going to go into all this because you're going to see it in a little bit. But one thing that might get overlooked is the demo kit manual. And so in this manual is the expertise of several very experienced physics instructors on how to do demos. So it's not just a demo kit, it's also a how to get the most out of demos. So the manual contains detailed instructions for setting up the equipment, the software, how to stage things, what could tips to keep things from going wrong, and questions to ask the students. And so the key thing for demonstrations, there are several, but one key thing is to get students to make predictions, think about what's going to happen before they see it happen, and let them engage each other when they do that. And so there are 46 questions similar to this one I have down here that you could put up on your screen or somehow distribute to students, and they answer before they see what happens, and then afterwards they see what happens, you discuss it. It's a powerful way to help students learn. There's a couple of videos we made about the demo kit. One for in the classroom use, and you might consider doing these online, like sort of that's what I'm doing today. And then the demonstration manual isn't online, but each demonstration has a link that gives you everything you need with it. And so one demonstration at a time is listed here. And so you can access everything and more than what's in the manual. And so again, those links are in the slides, which you can download. I think I put it, it's later on, maybe I think it's in the chat, but you can get these slides with those links. And Glenn's putting the links in there as he always does. So you can see all the stuff that comes with it. And so instead of spending time pointing all that out, let's just go ahead and start using it. And so our first demo is using the ballistic cart accessory. Ballistic cart accessories have been around for a long time, but this is the smart ballistic cart accessory, and you'll see why we call it that in a little bit. It has some features that other ones just don't have when it's paired with a smart cart. It does work independently, but with the smart cart, which I'm going to be using today, there's some other things you can do. And so on each slide for each demo, I just kind of gave a summary of what's in the manual. And so here you're just going to demo the cart when it's sitting still, then when it's moving, and then through a tunnel with and then with and without the tunnel. We'll at least go up through the tunnel. And so let's take a look at it. And so one thing you can do is adjust the size of the camera view. So right now, instead of me, you're seeing the track and, well, I guess you see my arm and the ballistic cart and smart cart. And if you want to make that bigger, there's a little handle between the screen and the camera view. Now I could stop screen sharing, but I want to show the capstone files as well. So I am going to keep screen sharing. So let's open up the capstone file. And so there's a file for each demo. You don't really need it. It's some are more helpful than others. But this one opens up, and really all we're doing is using the ballistic cart control panel. And this little warning sign is telling me I haven't connected to the hardware yet. So the first thing you want to do when you start one of these capstone files is click on hardware. And then over here on the smart cart, I'm going to press the on button. And maybe it's a little hard to see. Oh, let's see. Got a better camera. There we go. But the ballistic cart started blinking ready, and the Bluetooth connection light on the smart cart started blinking red. A little hard to see because of the ballistic cart in the way, but it showed up here on the list. So I click on it and it will connect and detect that I've plugged in the smart cart. So if you watched one of the videos, we give you more detail on setting things up because I want this to work. I have it all ready to go. But what I did is I just attached this to the smart cart using these black attachment screws. There are holes right in the top of the smart cart, and it's on there securely. And then I wanted to aim it. So there's two red aiming screws that you don't want to touch unless you're trying to aim it. Sometimes you accidentally grab those and start turning them. Don't want to do that. And this one tilts the cart side to side, and this one back and forth. And so what you do, let's go back to this camera view, is to set it up, I put it in the part of the track that I want the ball to be launching roughly. And I just push the ball down. Now it's locked in. And you want to be careful because it comes out. This is the highest launching ballistic cart that I've ever seen. And so it's coming out with a little bit of speed. So you don't want to look down in there once it's, well, really always assume it's loaded, right? It comes with, you should be wearing safety glasses when you're using this. I have regular glasses that should work. And then there's a manual release button that's based on a timer. So I can put this on a regular cart and it'll work. But here I'm just going to press the time release and it launches it up and it came right back down. If it landed a little bit on this side, I would use the aiming screw to tilt it a little bit away. If it landed forward or back, I would use the other aiming screw to tilt it, and that's what I did. Actually, in a way, I've got it almost aimed too well because it landed almost right back in the hole, and sometimes it'll land there and jump out. You really want it to hit a little off to the side because there's a no bounce pad that it takes the energy out of it and it keeps it from bouncing. So we have it working there. And the first thing you might do with students then is ask, well, what's going to happen if the cart is moving? And that's one of the questions that goes with the demo. Is it going to land back in? And after they make their prediction, you can have them hold up a card saying what their answer is, A, B, C, or D. There are software utilities that will let them share their answers and collect the results and tell you how many students picked each answer. There's an online thing called Poll Everywhere that lets you do that. A lot of different options for that. So I'm going to press the time release button and then give it a push. And it landed back in. Now, when they see that, their eyes kind of follow the cart, and to them, they think the ball went straight up and straight down, even though we know it took a parabola. So we came up with a trick for showing that it was following a parabola. We have it go through a tunnel. And to go through the tunnel, it's tricky to do with the time release. And this tunnel that I made is just out of a recycle bin. I just cut sides on it big enough for the cart to fit through. And so it just sits over there. So this does not come with the Smart Cart demo kit. You can make it out of just a cardboard box, it'd be fine. And then make sure it goes through without hitting. But the problem is I've got to get it to launch the ball just before it goes through the tunnel. So what I do is with Capstone, well, first I lock it. When I hit record here, it's going to zero the position sensor on the smart cart. And if we go to the settings for ballistic cart, it's set to trigger on a position 0. So and I could trigger it now if I wanted to. So when I hit record, now it's at 0, then I'm going to back it up. The next time it goes through 0, it's going to launch. So I hopefully put it at a good spot so it'll launch and the cart will go through the tunnel and then the ball will land back into it when it gets to the other side. How about that? And so it works live. Does that happen every time? Well, I've been here getting ready for this webinar for a while, and I did spend a good time practicing that, but the problem I have is the way I'm reaching over here and stuff. If you're doing it at your front lab table in front of the students, your demonstration table, it's a lot easier once you get it going. But I will tell you, don't move the track or anything once you get it all set. Then it's pretty much going to do it every time. And well, let's see. So one thing I have to watch, it'll trigger again the next time it gets to that spot. So I could just cock it and do it again. But when it hits the end of the track, the wheels might have spun a little and zero position might be a little different than I thought. So I like to, especially when I'm doing this, live for a webinar, is hit stop and then re-zero it if I'm going to repeat the demonstration. You probably don't have to do that, but anything that can improve success is worth doing. Twice in a row. So it is possible to get pretty good success even though it launches that high. The next demo with the ballistic cart, which we're not doing, is you set this up on an incline. And it turns out it will land on the incline, but it's worth resetting or just testing it first before you do that. And that's all explained in the demo. If you're thinking to yourself, gee, how on an incline wouldn't the ball not land back in? It turns out that the ball and the cart both have the same acceleration parallel to the track. And so it actually does. But a little trickier to do. And again, if you're worried about it, it's all in the demonstration manual. So any questions on the ballistic cart, Glenn?
None yet, Dan, but we encourage everyone to ask them in the Q&A panel.
Wondering how often it works like that. And pretty often, 2 in a row, that's doing, well, actually 3 in a row if you count the one without the tunnel. You can see a different tunnel, the fancier one that we use here at Pasco too. So the next one is using, I think it's one of the most engaging accessories for the Smart Cart. And of course it has the word smart in its title. It's the Smart Fan. And we've been selling fans that fit on carts for a long time. And people like them because it's a different way to produce a fairly constant acceleration without having strings tied to it, with going over a pulley with a falling mass, which is great. We do that too, but it just adds complexity maybe. And then just the fans are kind of engaging. So this is the fan and it clips right onto the Smart Cart. And let's see here, I want it going towards you. So one thing you want to do, probably, you can almost make it work if for whatever reason you want to do it the other way, is the side with the accessory cable, you want on the side with the accessory ports. And that way, also the way the fan, its default direction is positive, we'll have the Smart Cart going in the positive direction. So again, if you want to learn more about the fan by itself, go to the product page on pasco.com. This is more, we're trying to get through all the different accessories, but you'll get a good idea what it does here as we go through this demo. So let's open up the file that goes with this. There's several fan demos. So this one, first, again, we have to connect because I quit Capstone. I've just kind of learned when I do a bunch of different demos, it's a good idea to quit and start over. In class, I probably wouldn't bother doing that. but you don't usually use so many different sensors at a time in class like we would here at Pasco for a webinar. So once I connect to the smart cart through using wireless Bluetooth, it detected that I have a fan, and this is the fan control panel, and I can set the thrust anywhere from -100 to +100. And then there are advanced options for start and stop conditions. And you can also control it using our Blockly programming, which this webinar is not about that, but if you're interested in that, let me know. But you can program the fan to move the cart back and forth and prevent it from hitting the end stop. That's one of the things you can do with it. You can program it to increase the thrust at a regular rate, trying to get a change in the acceleration rate. So a lot of cool things you can do, but we're just going to be turning it on and off here. So I don't even need to hit record, but we want to look at the velocity time graph to measure the acceleration. So that is the first question with this demo is, there we go. First question with this demo is, what is the significance of the slope of the velocity time graph? And we'll see that we can tell by the units. So the first part of the demo is just to have the cart move down the track with 100% thrust. Now it takes a while for the thrust to build up. So if you really want to see constant acceleration, when I hit record, it's going to, because this auto's checked, it's going to just start, hopefully. But I hold it until it builds up to the highest level. And I stopped it there at the end. So if I didn't do that, well, it's you know, if I didn't do that, I'm just going to hit record and not hold on to it. So that's cool in itself. Then you get a changing slope, but for this demo, we don't want that, but that is a cool thing about the fans. So this is the velocity time graph. You can see pretty constant. Maybe there's a little bit of a curve there because the thrust does change as the cart moves relative to the air. And I can get the acceleration by clicking on that, the selection tool, and selecting just the part where the acceleration's constant. And then I can do a linear fit, and the acceleration is 0.643. Second part of this demo is ask students what's going to happen if we put some more mass on it, in this case, a ½ kilogram. So if you look, the cart mass tray is still available even though the fan is on there. And so that's the kind of feature you get when you have people who have taught physics designing our equipment, because otherwise you wouldn't know that that's what teachers are going to want to do. And so now I've essentially tripled, or not tripled, not quite tripled the mass, because the cart is 0.25, and then the fan is another couple 100 grams or so. So the question now is, what's going to happen to the slope of this line? What's going to happen to the acceleration? Is it going to go up? Is it going to go down? Is it going to stay the same? And easier to do if you're doing this at your demonstration table than what I'm doing here. And so we have our second graph here. Let's get rid of the other one. So it's 0.643, right? And so I can select that. And the slope is 0.356. And you can just tell by inspection that the slope here is different than the slope there. When I do this as a demo, and I'm not talking during a webinar, I would try and release it at about the same time And then both these lines start in about the same place. A little easier to see that they have different slopes when you do that. I'll try and do that for this last one. So last one, now we take the masses out. Or you can do this in whatever order you want. And we're going to make the thrust 50%. Now you have to be careful when you say 50%. Thrust is often used to describe the force, but in this case, it's RPMs. And so even though I cut the thrust in half, the force is not going to be in half. It turns out it's usually about a third. But that's not part of the demo. They're just asked what's going to happen to the acceleration. And so notice this one starts a little after 3 seconds. So I'll hit record. And once it gets there, I'll let go about there. So a lot easier to see that the slope is even less than this one where the mass was the same as well. You can do numerical versions of this. There are labs posted online for the Smart Fan, but this demo is really just a qualitative look at what happens, not quantitative. You can measure the force using the built-in force sensor on the Smart Cart, and then use that to derive Newton's second law, all kinds of great things. But that's this demo, all there is to it here. So any concerns or anything, Glenn, up till now? Pretty straightforward.
No questions yet, but they can ask them in the Q&A panel if they have them.
So the next one is using the fan again. So you might, guess the fan is one of my favorite things. It's definitely one of the most fun things I've worked with here at Pasco. So this one is a Newton's third law, but anytime you're looking at a dynamic situation, you're including all of Newton's laws. That's one of my pet peeves is questions that say, here's a system, which one of Newton's laws applies to this? It's going to be all three. Maybe some are more obvious, but it's all three. But to explain this, you're definitely going to have to understand Newton's third law. So we have, this one is more talking about how the fan works. Why does it propel the car? And so the first question, you just show the students the fan and how it propels the car, and you say, how is that working? And so we know that the fan blade is pushing on the air, and Newton's third law says that means the air has to push back on the fan blade with a force equal in magnitude, opposite in direction, and simultaneous. It's not like one thing happens then another. They happen together. And so that's the force that moves the car, is the air pushing on the fan blade. So it's important to make sure they've thought that through before you go on with this demo. So I'm going to open up the capstone file and connect again. I think it's still on. There we go. So to get this one to work, I've leveled the track pretty well. The track has 2 adjustable feet with actually there are 2 feet on each one of those. And so I put the cart in the middle, and if it started to roll one way or another, I would adjust the heights of these until it stayed put like it is now. So for example, if I put it there and it started to roll forward, well, then I either would raise this one or lower this one. And it's a little tricky to do that because you're looking down on the opposite side of a screw. And so students may know righty-tighty, lefty-loosey, but when you're looking at the other side, it can get confusing and they'll end up never being able to level the track. And so what I remember is righty-raisey, lefty-lowery. So if I turn these to the right, it's going to lift that end of the track and raise the track. If I turn them to the left, it'll lower that end. And so I did that already. It's adjusted. So after demonstrating how the cart works, we bring the fan out, which the sail that goes with the fan that comes out. And notice there's a Pasco label on it. And the first demo we're going to do is, you don't necessarily tell the students this, you just put it on, but you want the Pasco label facing the fan. And you ask the students, now what's going to happen? Is the cart going to go faster with the sail, slower with the sail, or is it going to be the same? Those are the three choices I usually give them. You might be thinking of a fourth choice, but it kind of falls under those categories. And they have trouble with this one. And so a lot of times I will make sure that they also write down why they're picking what they did. This one would be tough for them to put a why, I think, sometimes. So just get them to stick their neck out and pick something. Another approach to this is just to ask students what all the possibilities are without giving them to choose. And then they're more willing to volunteer their ideas, because they're not saying this is what's going to happen. They're just saying, hey, this could happen. And then they pick from those possibilities. That's another approach to this sort of prediction, because it can be intimidating to be asked to predict what's going to happen here. And so to get it going, on the SmartFan control panel, notice 50% is on here. If you do this with 100%, it's a lot harder to get to work. We found 50% is pretty, well, not work, but do what you expect it to do. Let's put it that way. And I'm just going to click on to turn it on. And so any student that said it was going to go slower is correct, as it's not moving at all. And you could have a great discussion about why that is. And if you start looking at the forces, we still have the fan blade pushing on the air and the air pushing back on the fan blade. That force is still there and pushing forward. But if it's not accelerating, there has to be an additional force now. And we know that's the air pushing on the sail. So the sail has, it's positioned in a way so that I get about the same force pushing that way from the air on it as is pushing on the fan blade. If you were to cut a hole in the sail, then what would happen? Well, you probably don't want to do that. In my classroom, I had a homemade sail I used, and I did have one with a hole in it, but I found with this, you can just take one side off. There are these two, I should have shown you that. There are these two holes on the cart that this fits in. I'm just going to put it in one of those. And so now the sail isn't catching all of the air. And so the force of the air on the sail might not be as great as the force of the air on the fan. And it does move. But in the demo kit, what they tell you to do now is flip the fan around, the sail around. I keep calling it the fan. It's the sail. And if you notice, there's a curvature to it. There, you can see it. And so now the air is going to hit and bend some of it. What is that going to do? So it's up to you how much you tell the students that. The one I used, my homemade one, was obviously curved. So I think telling them that, you don't necessarily have to say how the air is going to respond to that curvature. It's up to you. So that's the only thing that I've changed. There we go. Back to the, oh, you didn't see the, yeah, didn't see the other one. I see. So I showed you how I set the sail up, then I didn't do it. So here we go. It still might work. Now, this is how I had it. This is the part you didn't see. So now, even though the sale's there, because I took one post off, the force on the sale isn't as great. So thanks for bringing that up. Now I'll flip it around. Oh, it started to go. Try again. This is, it usually works. There it goes. Come on. So I think I have the track isn't quite level. So you can see how important that would be. Let's test it out. I'll flip it around. Be harder to see what I wouldn't do this with students, but yeah, I have the track a little not as level as I wanted. So it's going backwards now. So it's going like this. So what's happening is the air is, one way to think about it is it's bouncing off the sail. So before it was just hitting and stopping. Now it's hitting, stopping, turning around and going back the other way. At least some of it, the part that's curving off the side. So we know that's a bigger change in momentum. So if you just have an object hit something and stick to it, there's a certain change in momentum. If it hits and bounces backwards, the change in momentum is greater, and the resulting impulse and force is greater as well. So now the force of the, let's get it to work, righty raisy. There we go. Let's see if I can. There we go. So it's going the backwards now because the force on the of the air on the sail is more than the force of the air on the fan. So definitely check that out ahead of time, adjust everything, but I just had it a little bit off. Usually works pretty well. And again, you'll notice if you download the slides, I have, what happened there? If you download the slides, you get these links, which just go to directly to the demo files. But if you go to the all demo link, that's really the only one you need. And Glenn put that in the chat. That has a whole list of all 16 demos with the capstone file and the instructions, the questions, everything. So somebody's asking, can you measure the force on the sail? I mean, indirectly, because the acceleration of the cart you could measure. And then you can measure the force from the fan, but I think it's going to change a little when the sail's there. So if you measure the force from the fan without the sail, and then assume it stays the same, that it probably doesn't. So you would have to make some assumptions on that. Yeah, I can't think of a way to do that easily, but definitely the force from the fan, what I've done is put the hook that goes on the Smart Cart force sensor, and just you have the fan push the cart against the end stop and measure the force, and that works pretty well. So you can measure the fan force, and then when the sail is like this, it would be the same. But when you turn it around, you get a little bit more force this way. So all I can think of is measuring the acceleration of the Smart Cart, but that's very small. I'm definitely going to try that, but not live in a webinar. We'll let you guys try that one yourself.
Dan,
yeah.
Barbara notes that you're using Capstone for these demos. Could SparkView be used instead?
So SparkView works great with these, especially the ones I've been showing. But Capstone has a feature called workbook pages. We're going to see that in the next demo that makes it, if you're doing a whole string of different demos, it makes it easier. But when you start up SparkView and you have the fan connected, you'll see the Smart Fan control panel, and you can do all the settings you need to, and the settings are described at the end of each demo. Not, with the fan, it's just the thrust. And the next one, we're going to see some fancier settings where that's why I picked Capstone to use. It does give you some advantages. But no, I did all these demos with SparkView as well. Just doesn't have the workbook pages that work the same way. So now for simple harmonic motion, I'm going to use the blue cart, which has the force sensor hook on it. And I'm going to tilt the track and hang the smart cart from the track. And to help it now, the smart cart can measure the velocity and the acceleration and the force in simple harmonic motion, and we'll do that. But for a demo in front of a whole class, we have this accessory called the vector display. And it attaches right to the smart cart and has the same accessory cable as the other things we've been using. And it also is taking the smart cart measurements and displaying them as an LED light. Here, maybe it'd be better if I showed here. There we go. And if I move it, you can see it's getting the accelerometer measurement from the smart cart. So I can do demos with this, like I can hold it in my hand and spin around in a circle and show them the direction of the acceleration. But in this case, we're going to show a cart on a track, and the spring does not come, or the track doesn't come with the demo kit. So you can use pretty much any spring that you have. And what I'm going to do is adjust the tilt of the track and the mass in the cart until the equilibrium position is about in the middle of the track. So looks like I'm going to just lower the angle a little. And so where the equilibrium position is, I'm going to move the track foot because I don't need it there. So you can see where it is, and so students can see where it is. Maybe put a little white sticker on it so it's easier to see. And students would be looking more face on here. You're looking kind of at an angle. Maybe I can improve that a little bit. There we go. So now I have a simple harmonic motion system, but it's not connected to Capstone yet, so I can't use all the sensors. So I'm going to start up the Capstone file or SparkView file, but you're going to notice this one has a lot of features on it because this is a more extensive demo. So first, let's connect to the smart cart. And so we start out asking questions about the velocity. And on this first Capstone page, if I look at the vector display control panel, which would display in SparkView as well, I can select what measurement I want, but it's already selected for me velocity to go with the first question. And then the range I use, I adjust that so that as many of the arrows will light up as possible, but not saturate it. So if you're making your own demo, you can try these 3 different settings out, but we figured out 0.5 meters per second works pretty well for this demo. If you want to change the sign, that would be if I flip the vector display around. You might want to do that, but rarely would you want to use that. And so that's all I need to do is open up that workbook page, and it's configured for velocity. And you can see, hopefully, that the velocity display points in the direction it's moving as it goes. And so we start out kind of easy. Where is the maximum velocity? And we can see that it's when it goes through the middle. And if I click on the next page, there's the next question, which you could display up on your projector if you want. And it's saying, where is the cart when it's got 0 velocity? And then you just do it. Oh, it's 0 at the bottom and the top. And obviously, we'll see this. The smart cart can also display a velocity graph, but this way they focus on just one thing at a time. Then if I click page 3, now we're looking at acceleration. And notice, if you can tell, the smart cart now has a little A that's lit up because the workbook page told it to switch to that. If you're using SparkView, you would have to go in here and change that to acceleration. And then also notice there's 2 choices: acceleration using the position sensor or acceleration using the built-in accelerometer. So that works, but we're using the position sensor. And that also just reminded me, we're going to be going to force in a little bit. And so you want to 0 the force sensor when it's at the equilibrium position. And this, again, is all my mistake here is I'm not looking at the demonstration manual, which has all these steps in it. So I'm going to 0 out the force sensor before I make that mistake later. And so now they're asked, where is the cart going to have the maximum acceleration? Well, the maximum velocity was in the middle. So some students might think that's where it's going to be. But we can see that it's not. It's at the top and the bottom. So it's kind of opposite of what the velocity is. And then if we go to question 4, the question is, where is it going to be when the acceleration is 0? And we know that's at the equilibrium position when the force of the spring is equal and opposite to the force, the component of gravity pulling down and parallel to the track. I think I was giving it too much amplitude before. The velocity was kind of maxing out. So you can, with this one, you can adjust the amplitude, or I can adjust this. So let's see what happens if I put it on 5 meters per second. Well, now it's hardly lighting up. Maybe if I give it a really big amplitude, we might get a couple arrows. No, not really. So you can see the importance of making that setting right. And using a good amplitude.
Dan, Matthew has an interesting thought. Is it possible to put 2 vector displays on a cart so you can see, say, velocity and acceleration simultaneously?
You can't put it on the same cart, but we did that at one of the conferences in our booth, and we stuck 2 carts together because they have Velcro, and we put one on each cart, and that was pretty cool. So you can show both simultaneously, but there's only one accessory port on each smart cart. That, yeah, so yeah, you're going to have to use 2 carts, but that worked. And everybody wants as many smart carts as they can get. So just have to get that second cart and second display. So Then there's question, this gets a little bit more complicated. When the smart cart is going from B, the equilibrium position, up to A at the top, which of these statements is true about, is true? And so the acceleration velocity point toward B, they both point away, or they point in opposite directions. And the velocity is obviously going to be pointing in the direction it's moving, so that you can sort of figure that out. But that is a complicated question here. So you can see the acceleration is pointing down the ramp when it's there. And if you go and pick velocity, it's pointing up the ramp when it's going from B to A. And then 6 is about the force. And so where is it maximum? And they might get that it's maximum down at the bottom when the spring is stretched the most, but they may have trouble that it also has a maximum magnitude up at the top when the spring isn't stretched hardly at all, because now it's the mg sine theta that's dominating, which we know is causing it to go down the track. And then another one going from B to A about acceleration and force and velocity. So this one, give them a lot of time to answer this one, or you might come up with your own version, maybe even split it up. But this is sort of putting everything together here at the end. I think they can figure out the force and acceleration are always in the same direction. And where the maximum velocity is where the minimum acceleration of force is. So when you're ready to put it all together, the last page, we're not using the vector display anymore. And I haven't been saying record, but now I am. And you can show graphically all the relationships they were just getting from these demos, that wherever the velocity has a maximum positive or maximum negative or maximum magnitude, however you want to say it, the acceleration is 0 at those points. When the velocity is going, has a positive slope, you have a positive acceleration, or it has a negative slope, negative acceleration, and the force is kind of the mirror image of the acceleration. Because we know F equals ma, it's a vector equation. They have to be in the same direction and they're related to each other. If it was a 1 kilogram mass, then even their values would be the same, different units, but the numbers would line up anyway. And you can also display the position if you wanted to here, to show position, velocity, and acceleration, all the kinematics. You can see how it just shifts. That's something that is a little more advanced. So let's move on here. And we're going to take the vector display off. And this is something, if you have smart carts, you may not realize that you also have an electronic scale. So you can hang things from the hook and, like, scale at the grocery store. If you have a way to attach it to a ring stand or something, you could get a clamp or something. But one of the things that comes with the demo kit is our rod stand adapter. And it has a couple of screws on the side that I take out. And you can see the holes on the top of the, let's see here, I can do better there. The holes on the top of the mass tray on the top of the cart I can put the rod stand adapter on and attach it securely. One screw does it, but might as well use both. And then there's a hole and a screw to attach rods either that way or that way, depending on what you want to do. In this case, we're going to attach it this way. And so now I can put it on this clamp and hang things from it to get the force of gravity on them, their weight. And so this demo is about buoyancy. We're going to measure the weight of this brass cylinder in the air and in water. So first we want to zero the force sensor. Oh, I got to connect to the smart cart. So the force sensor is a little temperature dependent. They don't always go back exactly to their original position. And so if I hit preview here, which displays the force, it's not reading 0, even though there's nothing on it. It also will vary depending on the orientation of the force sensor, because it'll be measuring the weight of that hook, whether it's pulling or pushing on it. So you do want to get in the habit of remembering to 0 it. And so if I hang the cylinder, I can get its weight. And I can say keep, let's close that. I can say keep sample. And so there is the weight saved in the data table, 2.08 newtons. And then you can ask students what will happen to it if I submerge it in water. Will the weight go up, stay the same, go down? And then they see it live. And it wiggles around a little bit. As I shook it, you could try and stop it. It's kind of hard to, takes a little bit of time to get, it's varying by, 0.01 newtons here. And so now we keep the sample. And so the difference between those two, the student should know, is the buoyant force. So you can get a little quantitative. So this is the one demo where we're using numbers from the force sensor. That might be a quiz question. I just gave it away, darn. And so the difference between those two is 0.29 newtons. So that would be the buoyant force, but we could also check that by measuring the weight of the water that that cylinder displaces. And so to do that, it's a little fancier stuff. I have an overflow cup. This does not come with the demo kit. You can make your own pretty well. The key thing is put a little bit of soap in the water so that you get rid of a lot of the surface tension. You get more accurate values. So I'm going to put it here by this little paper cup that I have hanging on the, I know we're almost out of time, so and so I'm going to add water to the overflow until it starts coming out into the cup. So it comes out that little spigot. And well, it's really not cooperating. There we go. So it drips for a while. At this point, accuracy versus how long it takes to watch water drip. I'll leave that up to you with your students, how long you'd wait. But when it gets going pretty slow, what I'm going to do is zero the force sensor. And then I'm going to submerge the cylinder into the overflow cup, and any additional weight that goes into the cup will be the water that it displaced. So I'm going to zero it, and I'm going to lower it using this other rod so I don't have to hold it. And you could put it on the bottom of the cup. I'm just thinking students will think that makes something different. Maybe that'd be a good extra question. So I have it so the cylinder is suspended above the bottom, just trying to eliminate more variables. And it's going to drip for a while. Typically, when I let it drip for a while, I'll get 0.25 newtons. I don't think we have time to wait for that. And when I calculate it using the volume of the cylinder, I get about 0.24, 0.25. And so we're kind of off this time. 0.29 is what we got here. I got 0.27 when I did it earlier. So it's not the most accurate thing in the world. I think I'd like to do it on a bigger scale and then see how that goes. Because using 1/100th of a Newton, you're pushing the limits of this thing. But it's already up to 0.24 now. So that worked pretty well. And again, there's a, oops. And so there's a slide showing that. But again, I'm just summarizing what's all in the demo kit manual. I think I even put a copy of the full manual. I'm not sure I'm allowed to do that. So Glenn, don't tell anybody. But that is at the link where my slides are as well. But you can get each demo's files by themselves as well. So that is it. There's the link to the files again. And I'm not going anywhere. So if people have questions or comments, I'm happy to help Glenn out with that. But otherwise, we are done. And I'm going to stop recording here. I can. Okay.